minus 1 is going to be 2. All these numbers are present in the domain, but the very first natural number 1 does not have the preimage. As 1 does not have the preimage, 1 remains free in the codomain. Therefore, in that case, there is one element which does not have the preimage. Therefore, this function will not be a onto function. So here the conclusion can say, for all y belong to R codomain, there do not exist at least one x belong to n domain such that f of x equal to y. Therefore, in this case, f is not onto. F is not onto. So, obviously, the word onto means all the elements of the domain need to be on to the elements of codomain. That means there should be no free element in the codomain. All the elements of the domain should be on to the elements of domain. So, if on to elements of domain, codomain means all the codomain elements should be covered. There should not be any free element in the codomain. So, obviously, the function is called as the onto function. So, these are the few problems where you can check whether the function is going to be onto function or not. It should be done purely based upon the observation. First, you try to get the preimage rule and try to substitute some numbers from the codomain and check whether every number in the codomain do have a preimage or not. If at least one number do not have a preimage, the function will not become onto. If every element in the codomain do have a preimage, at least one preimage, then the function becomes a onto function. So, which you can give the conclusion. So, these are the various types of example sums which come across in the examination regarding the onto function. Now, we will discuss about the main points about note regarding the onto function. Some important note regarding the onto function. Here in this note, we are going to learn the formula to find the number of onto functions from set A to set B. In the previous class, we have seen the total number of functions possible from set A to set B, and also we have seen total number of one-to-one functions possible from set A to set B, and also many-to-one functions possible from set A to set B. Now here we are going to see about total number of onto functions possible from set A to set B. So for that, first thing is the condition is required. So one-to-one onto functions are possible only when onto functions are possible only when n of A is greater than or equal to n of B. If n of A is greater than or equal to n of B, then only the onto functions are possible. As we have got the same kind of condition in the one-to-one functions. One-to-one functions are possible only when n of A is less than or equal to n of B. Similarly, onto functions are possible only when n of A is greater than or equal to n of B. What happens if number of elements in A is less than the number of elements in B? Imagine that I'll take only 3 elements in set A and I'll take 4 elements in set B. What happens in this case? That is, if n of A is less than n of B, what happens in the case of this? Does the onto functions are possible or not? In this case, obviously, if I want to make it as a function, obviously I can make it a function like this. But here this will not become an onto function, because as per the definition of onto function, every element in the codomain need to have at least one preimage, but some of the elements are remained. Why the elements are remained? Because number of elements in A are more than number of elements in A are less than the number of elements in set B. That is the reason some of the elements are remained. If it is reverse, obviously if 6 and 7 are not there, obviously what happens is n of A is going to become greater than n of B. In this case, every element of the codomain is having at least one preimage, therefore it is going to remain as onto. So whenever n of A is less than n of B, number of onto functions become 0. So onto functions are possible only when n of A is greater than or equal to n of B. So this is a very important point. So note number 2 is number of onto functions from set A to set B when n of A is less than n of B is 0, that is onto functions are not possible when n of A is less than n of B. So in case if I give you an example, say n of A is equals to 2, n of B is equal to some 3. So how many onto functions are possible? In this example, n of A is less than n of B. Because n of A is less than n of B, the number of onto functions becomes 0. That means it is not possible to form an onto function in the case when n of A is less than n of B. But what happens if n of A is greater than n of B or equal to n of B? So in that case, we need to go with the formula. Let us see now how to get the what is the formula to find out the number of onto functions. So the derivation of the formula is you'll learn in your higher classes, but right now the number of onto functions if n of A is greater than n of B is given by number of onto functions from set A to set B, where n of A is equal to m, n of B is equals to n, is given by n to the power of m, that is number of elements in B to the power of number of elements in A minus nc1 into n minus 1 to the power of m plus nc2 into n minus 2 to the power of m minus nc3 n minus 3 to the power of m plus so on. So the number of terms should go on as much as possible. So here we are going to use the formula of combination. The formula for this is going to be NCR as a formula for combination. As how we have used the formula for permutations for one-to-one function, here we are going to use the formula of NCR, which you are going to learn in your higher classes, but right now you accept the formula. NCR formula is going to be n factorial by n minus r factorial into r factorial. And here obviously we can have the formula NCR is equal to n factorial by n minus r factorial into r factorial. So wherever required NC1, NC2, NC3, we can make use of this formula and substitute it, you can get the number of onto functions. Let me go through some example here how to solve it. So as I told you, the example here, let us suppose that n of A contains that is n of A should be greater than or equal to n of B. N of A contains say 3 elements, n of B contains say 2 elements. Then what is the formula or number of onto functions given by this formula? So it is going to be m value, it is going to be n value, that is here m is going to be 3 and n is going to be 2. So the number of onto functions is given by this formula. So I can substitute the values in the formula. Number of onto functions is given by n to the power of m, that is 2 to the power of 3 minus nc1, that is 2c1 into n minus 1, that is 2 minus 1 whole to the power of m plus 2c2 2 minus 2 to the power of 3. And actually as the term is going to become 0, no need of writing the remaining terms. So because it is not required to write remaining terms, simplifying it, you get 2 cube is going to be 8 and 2c1 is going to be 2, that is obtained by using the formula of NCR. So 2c1 is going to be 2 into it is 1 to the power of 3 is 1, it is anyhow going to become 0. So we get totally is going to be 6. There are 6 onto functions possible from set A to set B in the case if A contains 3 elements, B contains 2 elements. So this is a simple example which I have solved it, so to get the number of onto functions from set A to set B. Say this is going to be the important formula to find the number of onto functions, and this formula is modified in the case if set B contains 2 elements. Observe carefully, in the case if set B contains exactly 2 elements and set A contains m elements, this formula is modified. That is, let's take some example. set B contains any number of elements, not a matter, but in set B if it contains some 2 elements exactly, how many onto functions are possible? In that case, we have to see a simplified or modified formula for this. Just substitute n value as 2. In the case n value is 2, we get number of onto functions would be number of onto functions in the case where set B contains 2 elements is given by n value is going to be 2. So 2 to the power of m, first set contains m elements, second set contains 2 elements, so 2 to the power of m minus nc1, that is going to be 2c1 into 2 minus 1 to the power of m, and next is going to be 2c2, 2 minus 2 to the power of m. As because it's going to become 0, not required to write the remaining terms. So we get the formula as 2 to the power of m minus 2c1 is going to be 2, 2 into 1 to the power of 1 is 1 only, so 2 into 1 is going to be 2. So the modified formula to find the number of onto functions, if second set contains exactly 2 elements, the number of onto functions are going to be given by formula 2 to the power of m minus 2. In this example, m contains 3 elements, so if m is 3, we get 2 to the power of 3 is 8, 8 minus 2 is going to be 6. That means in that particular example, if I try to trace out the onto function, there are 6 onto functions possible. Like here is going to be 1 onto function. In this way, if we go on creating the onto functions, we get totally 6 onto functions. So the formula we have seen to find the number of onto functions is 2 to the power of m minus 2 in the case if second set contains exactly 2 elements. If second set contains more than 2 elements, we apply the general formula what we have discussed earlier. So this is all about the onto functions. Now we have seen about the third type of function is called as onto function, and now we are going to see the fourth type of function called as into function. Let's go ahead with the fourth type of function. The fourth type of function what we are going to see is going to be called as into function. Into function. So we have seen in the previous class that is a function which is not called as one to one is called as many to one. Exactly same way, a function which is not an onto function is called as an into function. So the definition of this function is going to be is said to be an into function if it is not a onto function. A function which is not an onto function is called as a into function. Say for example, I have told you about what is meant by an onto function. A function in which the range is equal to codomain is called as an onto function. So in this case, if you observe here, the range is not equal to codomain. Because the range is not equal to codomain, here range is going to be equal to 5, 6, whereas the codomain is going to be equal to 5, 6, 7. So as the range is not equal to codomain, we can say f is not an onto function. If it is not an onto function, we can say f is a into function. So moreover, the range is denoted by f of a, codomain is denoted by b. So we can observe that the range f of a is not equal to codomain b. But what is happening here? What's happening here is the range is going to become a subset of codomain. That means here you can say that if the range is not equal to codomain, it's going to be called as into function, or if the range is a subset of codomain, the range is subset of codomain, then also we can say the function is going to be a into function. So there is no chance of range becoming a superset of codomain. So the only thing is it should not become equal to codomain. If it is not equal to codomain, the only option is it should become a subset of codomain. So the other definition of into function is a function f maps a to b is said to be an into function if the range f of a is not equal to codomain or the range f of a is subset of codomain. A function which is not an onto function is called into function. That's the simple definition, or otherwise we can go ahead with this. So the alternate definition what you have for into function is, the alternate definition is a function f maps a to b is said to be an into function if a range f of a is subset of codomain, or we can also say f of a range is not equal to codomain. So a function in which the range is subset of codomain or range is not equal to codomain, this kind of function is called as a into function. And we have seen about the fourth type of function called as into function. And now let us see about the fifth type of function, that's called as bisection. So a simple definition for bisection. So fifth type of function is called as bisection. Bisection or bijective function. So this is the fifth type of function, which is going to be the main type of function. So a function which is both one-to-one as well as on-to function is called as a bisection. Already we came to know about what is meant by one-to-one function. Already we have checked some problems where it is going to become one-to-one function. And also we have seen some functions which is going to become onto also. So now a function which is both one-to-one and onto is said to be a bisection. So a function f maps a to b is said to be a bisection if it is both one-one and onto. So any function which is going to satisfy the property of one-to-one function and is going to satisfy the property of onto function, then we can say the function is going to be a bisection. So let us check some example where the function may become both one-to-one as well as onto. So the questions can come in different manner. So let me go with some example where the question can be asked in this way. The first question: given f maps a to b is a function where a is equals to 1, 2, 3, 4, 5 and b is equals to a, b, c, d, e, such that f is equals to 1 comma b, 2 comma c, 3 comma a, 4 comma e and 5 comma d. Now here this question is asked. Now the question is here, is f a bisection? So if you want to check whether the function is going to be a bisection or not, we need to check whether the function is both one-to-one and onto. Such kind of problem we already have seen in one-to-one as well as onto. The same thing can apply here and check whether the function is both one-to-one and onto or not. As to check it is one-to-one or not, I have told you that see the second coordinates. If second coordinates are all distinct, we can understand that the function is going to be a one-to-one function. And in the case of onto, check whether the range is equals to codomain. Range is the number set of all second coordinates. Codomain is already B, which is also given to you. If the range is equals to codomain, we can confirm that the function is onto. So here the explanation for one-to-one. Here the second coordinates of f are all distinct. Therefore, we can say f is 1, 1. So we have got f is 1, 1. So because the second coordinates are all distinct, you can say the function is going to be 1, 1. Coming further, range of f. Range of f is set of all second coordinates. Set of all second coordinates are b, c, a, e and d. It's the range of f. What's the codomain of f? Codomain of f is going to be b. That b is also given as a, b, c, d, e. So what happened here is we got the range is equal to codomain. The range is equal to codomain. Therefore, we can say f is onto. So as because f is a one-to-one function and f is a onto function, we can confirm that f is a bisection, as f is both 1, 1 and onto. Therefore, f is a bisection. So this is one of the example for bisection. So whenever a question is asked based upon the functions of bisection or not, you need to check whether the function is both one-to-one and onto. Now let us check the important note regarding the bisection. Note 1. The bisections are possible only when they satisfy the condition of both one-to-one and onto. We know that one-to-one functions are possible from set A to set B if n of A is less than or equal to n of B. And same way, onto functions are possible only when n of A is greater than or equal to n of B. Now, if you want to require the number of bisections, or if you want to get the bisection, it should satisfy the condition of one-to-one and as well as onto. One-to-one function and onto function conditions are possible only when they satisfy both these conditions. So satisfying both the conditions means the only possibility is n of A is equal to n of B. So bisections are possible. Bisections are possible only when n of A is equal to n of B. So because it should bisection means it should become one-to-one and onto. So to make both one-to-one and onto, it should satisfy the condition n of A is equal to n of B. And number of bisections from set A to set B is given